Good morning, Internet friends, and welcome to the ElectionGuard design series. This first video is called ElectionGuard in Context. I've struggled a little bit with how to explain ElectionGuard to people who haven't heard of it before. The best way I've come up with so far is to build up a kind of abbreviated historical election tech stack. So first I'll talk about how you can conduct an election on paper in the analog real world and how nation states do it today, more or less. And then I'll talk about how you can add various electronic elements on top of that system. Then I'll talk about how ElectionGuard proposes to add cryptographic guarantees to those electronic elements. And then in a future video, I'll talk about how my project proposes to add blockchain guarantees to the ElectionGuard ones. So you can see we're building up a stack in layers, and at each layer, we're going to try to keep in mind the important security guarantees of the existing design and improve on them without breaking anything in the next layer. Before getting into the details of the voting workflow, I just want to be upfront and start by saying that this project isn't trying to create the ultimate slick voting app that everyone really wishes existed. There are good reasons why that's very hard to build, and maybe we'll get there eventually, but I think a more realistic approach is to start with what we can build now and incrementally improve it. What we can build now is traditional in-person paper voting with additional cryptographic guarantees. So we're not talking about mail-in ballots. We're not talking about voting at home on your phone, although I do have some ideas later about how you could use a phone app in combination with coming in person, but you still have to come in person. And we're not talking about any fancy new identity system. There are ways each of those could potentially be added in the future, but I think it would be a bad idea to try and add them from the beginning because, as you'll see in a few minutes, even this fairly basic sounding version turns out to be kind of tricky to implement in practice. There are a lot of details you have to get right. I'm of the opinion that when working on election systems, the right way to do development is to move slowly and not break anything. Specifically, the main thing we're trying not to break is the delicate balance that's been developed between auditability and voter privacy. It's pretty easy to imagine how you would build a system that maximizes either one of these individually, but getting them both up to a reasonable standard at the same time is much more of a challenge. Alright, with that in mind, say I'm a voter and I'm going to vote in a traditional in-person election. What would that look like? It varies a lot because there are thousands of different jurisdictions, but in general, the workflow would be something like this. I would walk in the front door and I would stop at a check-in or registration desk of some kind. And the poll workers there would confirm that I'm eligible to vote in this election and haven't voted already. So maybe they would cross my name off a list or something. Then they'd hand me a paper ballot and send me off to the voting booth. In the booth, I would read through the ballot and fill in the little bubbles or connect the arrows or however that ballot works. Then when I'm done, I just go back up to the front and drop the ballot in the ballot box. Let's take a look at some of the important security properties of this workflow. The first is that voting itself is publicly private, which means you can't see which bubbles I'm filling out, you can't see who I'm voting for, but you can tell that I'm not doing any funny business in the booth, like holding my phone up and vlogging it, or like taking pictures and texting to people about it, or anything like that. The second is that the ballot is anonymous. It doesn't have my name on it, and when it's counted later, whoever's counting it won't know who cast that ballot. Another important property is that the ballot box itself needs to be tamper evident, so you shouldn't be able to open it without breaking some kind of seal. Related to the anonymous ballots is that the registration, whatever process they use, can't be connected to the ballots. So the state will probably keep a list of who voted, but they won't have any idea which ballot each voter corresponds to. And then finally, a general property of all of these in-person things is that you should be able to observe everything. So there will sometimes be official independent observers, like from newspapers or representatives of political parties, or sometimes the candidates themselves will be like in the room watching, making sure that there's just nothing weird going on. Like nobody is turning away voters at the door or trying to intimidate them. Nobody is doing anything weird in the voting booths. Nobody's touching the ballot box, trying to open it, all that sort of thing. So it relies heavily on physical security. Okay, in a traditional election, my job as a voter is done now and I can just leave. At the end of the election, the people running it will take the ballot box, put it in a van or something, and transport it to a central location. There are lots of different ways to do the counting too, of course. I'll just show one reasonable method. Say we have a very simple ballot and it just has Alice and Bob, and you're voting for one of them. You could take the papers out, put them on a desk, and then look at each one in turn, hit the A or the B button, and put it in the done stack. And that way you can't mess anything up. Even if you're doing thousands of them, there's nothing you need to remember. This would actually usually be done with two people so that they can check each other, and then there will be more independent observers standing around watching them to make sure they aren't doing anything weird. The pros of counting by hand this way are that it's simple, which makes it more trustworthy. It's observable, which is another way of saying it's auditable, and it maintains anonymity, which is another way of saying voter privacy. The main cons are that having people count things is slow and error prone, and that there's a custody issue with how do you make sure nobody's messing with the ballot boxes in transit. Alright, so that's the old school method. How is this generally done today? It's basically the old school method still, with various computerized parts grafted on, and which parts will be computerized varies by jurisdiction. One thing you can commonly do is you can check voter registrations with a state database rather than having printed out lists of names at the polling place. Another common thing is that you can have a computerized voting machine. The main point of this is for accessibility. It makes sure that if you need a different language translation, or if you need the words to be really big, or if you need to listen to audio because you're blind, or all of those sorts of things, it's much more inclusive. And it also makes sure that you can't fill out the ballot wrong. When it prints you out a paper ballot, all the bubbles will be perfectly filled in. More interesting for our purposes is that you can also put a computer in the ballot box. The way that works is you scan your ballot, and then after it scans it, it also keeps the paper the same way a normal ballot box would. But internally, it has counters that increment. So say I vote for Alice, it'll increment the Alice counter. So what are the pros and cons of adding electronics like this? The first thing to notice is that even though we've computerized the registration check and the ballot scanning, they're still not connected, so we've maintained anonymity, so that's good. The second thing is that a computerized registration check is much faster than doing it on paper, and that's basically just because you don't have to print out thousands of sheets of paper and transport them to all the different polling places and sort them properly and all that, and flip through them while everyone's standing in line. It's also more flexible because since you don't have to do that, you don't have to pick a polling place in advance, so you might be able to go to whichever one is less busy that day. Another thing, it's not really a property of the computer system, but of the overall system, is that these things are modular. So a different jurisdiction can use a totally different registration system. Like one can be doing paper and one can be doing a computerized database, and maybe another one is very forward thinking and has fancy new zero knowledge proof ideas. And they all coexist because the registration isn't actually connected to the rest of it. The filling out of the ballot electronically, that's also faster, but more importantly, should drastically increase the number of people who can vote properly. What about the ballot box? That's also faster if you consider it as part of the counting rather than part of the saving the ballots. Incrementing the counters is much faster than waiting for people to count all the papers later. But this wouldn't really be acceptable if it was the only way we counted the ballots. It's too easy to hack any single machine, and it's too hard to audit because you can't really see the internal counters incrementing when you put new ballots in. And by the way, I don't mean anything bad about this particular machine, this DS200, or the company that makes it or anything. I'm just using it as an example. This is just a generally hard problem. So what people do is they also keep the paper ballots, and they treat the counters from the ballot box as a kind of preliminary tally, and then they don't call the results final until they've also counted it on paper. And that's a general property of all of these digital things when they're done right, is that if any of them fails, you should be able to fall back to paper. Other than the counter being incremented inside the ballot scanner, it's also still publicly private, so it maintains all the important properties of the in-person system. And of course, the electronic ballot scanner box is also tamper evident. You can probably guess how tallying has to work in this hybrid paper-electronic system, but I'll just draw it out for completeness sake real quick anyway. One simple method would be you start a spreadsheet, you have columns for Alice and Bob and rows for polling places or voting machines, polling place 1, 2, and so on. And you just fill in the totals by reading them off the machines first, and then you don't mark any of the cells as final until the paper counts catch up with it and confirm that they match. So what have we gained by doing this electronic ballot box part? The first thing is just that we have fast and usually accurate preliminary numbers we can report on election night, which is great. There are still some lingering issues, like the electronic ballot box being potentially hackable, and also that it's being driven around in a van for a while, maybe not watched that carefully. And the paper counts, we still have to do them, and they're still slow and error prone. But that's less of a big deal because we have the preliminary numbers, and it's good to be able to double check that they both match. And that actually makes the custody issue less severe too, because if you're going to mess with the ballot box, like stuff some ballots in it, you have to both physically mess with it and hack it at the same time, which is probably a lot harder than either one alone. So I'd say that this is not really intellectually satisfying, but going in a good direction and objectively improving the security of the system. Thanks for sticking with that really long-winded explanation so far. I know it was a lot of analog civics things, but I think it'll give you a much better foundation to understand ElectionGuard, which we're finally ready to talk about. For now, I'll just show the parts of it that interface directly with the legacy systems we've been talking about so far in this video. And this won't be anything like a complete explanation. It'll just be a first naive version or a skeleton of the process. And then we'll come back later and flesh it out with details and mitigations to several potential attacks. Let's get into it. I'm eventually going to propose a bunch of changes to this voter workflow, but for today the only thing that needs to be added is we need to install some new software on the ballot box scanning machine and maybe hook it to a printer. But it'll still be doing all the same things it was before. So it'll be scanning a ballot and it'll be keeping the paper copy, and it'll have internal counters that it's incrementing that show a running tally of each of the contests. But then it's also going to take the entirety of each ballot and save an encrypted version of it as a file. And then it's going to return the voter a receipt, and on the receipt will be a QR code or a URL that has a hash of that file. And you'll see what that's for in a minute. So this maintains all the important properties of the existing voting stack, and it can fall back to be equivalent to the existing stack in case something goes wrong, which is important when you're pitching this to local governments, of course. But we've gained this really cool new ability, which is that an individual voter can go back after the election and check that their vote was actually included in the final tally. And this is one of those things that once you see it's possible, it starts to feel kind of bizarre that we didn't always have this. But it's a new ability. And besides giving an individual voter confidence that their own vote was counted, it's also the first step on the road towards making the whole system more transparent and harder to hack at scale. Basically, this will prevent you from removing votes, and then we'll need to add other mechanisms to prevent illegitimate votes from being added. When it comes time to count the votes, we now have 3 different tallies going at the same time. First, we have the preliminary counts from the voting machines. And then we still have all the paper ballots that we're going to count by hand and confirm that the totals match the counts from the voting machines. And then we have these new individual encrypted ballot files. The way this part works is you first gather all of the individual encrypted ballot files from all the voting machines. So here I'm using 10,000 as an example. Say there are 10,000 voters. And these ballots are encrypted in such a way that you can actually add the encryptions together and come up with an encrypted total without decrypting them first. And this is a cool crypto magic thing called homomorphic addition that I'll go over in a separate video. But you basically aggregate them all into one tally, and then you separately decrypt the tally with the administrator's private key. So you end up with all the individual encrypted ballots and one encrypted tally, and then the plain text that corresponds to the tally. But you never individually decrypt the ballots, and that preserves voter privacy. Then the last step is just to package up everything into an archive. So you take the ballots and the final encrypted tally and the corresponding plain text and some miscellaneous keys and things, and you make a zip file of all of them. The administrator signs the zip file and uploads it to the government website. And that's what people will be able to download to check that their vote was counted later. Let's take stock one last time of the things we've changed so far. What have we gained by adding cryptography? One big thing is that having a receipt that you can use to check whether your vote was actually included in the total solves the custody issue. Or at least, maybe I should say it partially solves it. It solves it from the perspective of making sure your vote isn't removed, but we're still going to have to do something else to make sure that extra votes aren't being added. But it partially solves the custody issue. And then a bigger thing that we haven't really talked about yet is that if you look at these steps, every step after that point is mathematically provable. So the aggregation is provable and the decryption is provable. So as a voter, you don't really have to worry about anything nefarious happening during the tallying process at all anymore. You only have to worry that the right set of ballots were included, but adding them up into the final totals is all mathematically certain. And if we look at the pros and cons one last time, this whole tallying ceremony, even though it looks complicated, it's actually still very fast. It'll happen way before the paper counts are finished. The main downside is just that it's complex, but I don't think that's a long-term barrier because it's not more complex than other types of cryptography you use every day without noticing it. Like, this isn't a more complicated system than the HTTPS in a website, for example. It's just a new one that we're not used to, so I think that's actually fine. It also doesn't interfere with the other two types of tallies, so now we have 3 different tallies and we can check that they all match. So that gives us a higher degree of certainty. And I think that's probably a good place to wrap it up for today. If you watched this all the way through, I hope you now have a pretty good idea of the physical context and security considerations that ElectionGuard is trying to address. And I hope that you're also convinced that we can make meaningful gains by adding a cryptography layer on top of the paper and digital system we have today. If you're sharp, you might have noticed a few potential problems in the ElectionGuard system as I've explained it so far. And that's awesome. We'll talk about those in future videos. Another thing for future videos is I haven't mentioned anything about why I think this system should be hooked up to a blockchain. And I know that's a little bit non-obvious and controversial. So stay tuned. I'm excited to get into that too. And in the meantime, be excellent to each other.